All right, section 5. Now we're going to go in order. Section 5 is supposed to be the easiest question on the test. And just because I said that, half of you will get it wrong. I'm going to spend 20 minutes on this, and it's not that hard. It's just people treat it horribly. This is transformation of functions. So let's start off with an easy function. Here's f. -2. I want to make it decent. Trying to imagine where it would be. -2, -4. It might be too big. 0, 2, and 4, -2. 3 points. Let's graph it. Just a small one. It's just points. Now these are just the endpoints. We're going to connect it with line segments. So this is what's called a line segment graph. So -2, -4, he's over here someplace. 0, 2 is here, and 4, -2 is here. So I'm talking about this graph, line segment graph. So what I want to do is I want to transform this. And there's several ways of transforming it. I can move it left, right. That's called a horizontal translation. I can move it up and down. That would be called a vertical translation. I can flip it. That would be called a reflection. We could rotate it, but that takes matrices, so we won't get into that. We can make it thinner, fatter, taller, shorter, all those types of things. So that's what we talk about when we talk about transformation of functions. So I have to go through all the possible motions and manipulations of this function. So this is f of x. Okay. So what happens if I take my original function and I write, well, let's let g of x equal f of x plus 2. Now you have to interpret this the right way. This is that function notation interpretation which a lot of people have a hard time with. So basically what this means is I'm looking for a new function that takes my original function and adds 2 to it. Now when I talk about f of x, what value am I talking about? The domain or the range? The range, because this is equal to y. So I'm taking my y coordinates and adding 2 to it. So what happens is I get this thing called f plus 2, and it's going to be, the domains aren't changing. This is changing the range. So the domains are exactly the same, -2, and instead of -4, what am I going to do to it? Add 2 to it, so it becomes -2. And instead of 0, 2, it's going to become 0, 4. And instead of 4, -2, it's going to become 4, 0. And this becomes my new function. So when I graph it, I'll do it in blue over here, you get -2, -2, which is here. You get 0, 4, which is here. And you get 4, 0, which is here. So the entire graph, it's supposed to look like it just got shifted up 2 units. The whole thing was just picked up. The shape didn't change. Distances didn't change. It just got literally moved up 2 units. So if you take an original function and you add and subtract on the outside of it, all it's going to do is move up and down. You should know this from your test. Remember, you lost that +1, and your graph was down 1 compared to everybody else's. So that plus becomes really important. All right, 2. What happens if I take g of x and I say, well, let's let it equal f of x plus 2. Now the language sounds the same. F of x plus 2, f of x plus 2. But it's a little bit different. This is f of x plus 2. This one is f of x plus 2. So where one of the plus 2's was on the outside, number 1, this plus 2 is on the inside. That's kind of how you want to phrase it. And when it's on the inside, what is this piece called of the function? Is it the range? No, it's the inside part. This is the domain. So that's going to affect the domain of this function. Well, the domain of the original function is -2, 0, and 4. And f can only take -2, 0, and 4, so I have to adjust it in such a way that when I add 2 to it, I get back to -2, 0, and 4. So one way of dealing with this is, well, I need x plus 2 to equal -2. I need it to, because otherwise I'm not in the domain of the f function. I need to be in the domain of the f function. I also need x plus 2 to equal 0, and I need x plus 2 to equal 4.
You mean x plus 2 is 2?
-2. I need x plus 2 to be -2. I need x plus 2 to be 0. And I need x plus 2 to be 4. So it comes back to my original domain. So you can set up a table. Here's your domain that you're going to end up with. This is the number you're going to start with. And then you're going to do your f of x plus 2. And I do a lot of these with tables because they get kind of confusing after I put like several motions into it. So I want to get used to this. So I need this one to be -2, 0, and 4. Okay. So if this one's -2, what did x have to be?
0.
If I plug in 0, 0 plus 2 is 2, not -2.
1 and 4.
Solve this equation. Subtract 2 from both sides, you get x equals -4. To get 0 out of this, it would have to be x plus 2 is equal to 0, so x has to equal -2. And then finally, x plus 2 is equal to 4 means x starts at 2. So these are our plotted domains. These are the domains of the function. And when I evaluate the function, well, -2 gives me back -4. 0 gives me back 2. And 4 gives me back -2. But what I plot is a little different. These are the domains that evaluate f. These are the domains I'm going to plot. So the coordinate is going to be -4, -4, -2, 2, all the way from the left, all the way to the right, and 2, -2. I'll have to redraw the graph, but that's okay.
How did you get the f of x plus 2?
Well, it's here. I just made them
I mean, in the column.
because that's what I'm looking for, f of x plus 2. So f only works on -2, 0, and 4 as the domain. So it doesn't work on x plus 2, it just works on x. But I had to find the right value for x so that when I do plug it in for x plus 2, it gives me back -2, 0, and 4. So basically you take your inside and you set it equal to your domain. At least in this case, the 3 points. All right, so when I plot the old one, what did I use last time? Green for the old one? It was green. The old one is -2, -4 down here. Yeah, here. -2, -4, 0, 2, 4, -2. So this is the old graph. That's the original f of x. Now if we do f of x plus 2, we're going to plot -4, -4 here, -2, 2 here, and 2, -2 here. So what happened to the graph? It shifted 2 units to the right. Where this plus 2 moved it up 2 units, this plus 2 on the inside moved it left. You would expect it to move right because it's plus 2. So the trick is, if it's outside parentheses, it goes in the direction you expect it to go in in this case up. If it's inside the parentheses, it goes opposite the direction. In other words, what's going to make this thing equal to 0? And the only thing that makes it equal to 0 is -2, so it takes everything and shifts it -2 units to the left. So far, so good? Okay. I'll do it in black. 3. What happens if I take g of x and I multiply f by a negative? What happens to the graph? Am I affecting the range or am I affecting the domain? Or a whisperer. Stop that. Say it out loud. Feel confident. Range. It's on the outside. It affects the range. So what happens here is, if we do a little table, we'll have our domain, and then we're going to take the range and multiply it by a negative. Well, the normal domain is -2, 0, and 4. If I take the y values which were associated, the first one was -4. You know, it was -2, -4. But this negative makes the -4 positive. It's supposed to be 0, +2, but this is going to make it 0, -2. And it's supposed to be 4, -2, but this is going to become 4, +2. So what does that do to the graph? I'll try to put it in this one. I'll do it in blue again. It shouldn't hurt it too bad. So you plot -2, but in this case +4 would be up here. Instead of 0, 2, you're going to get 0, -2 down here. And instead of 4, 2, you're going to go, instead of 4, -2, you're going to go 4, +2. So you get this graph. So how does this blue graph correspond to the green graph? Flipped over what?
Shape.
I know the shape flipped over, but how did it flip over? The distance between the depth and the pinnacle of the green and the depth of the blue is the same, right? So it flipped over the x-axis. It flips over the x-axis. So by multiplying by a negative, this becomes a flip over x-axis. Later, I'm going to call it over the horizontal. But we'll come back to that. There is an order to these transformations, but if you say horizontal, there is no order. But if I say x-axis, I'll have to impose an order on it, and I really don't want to. The fourth thing we can do to these points. Oh, so let me write this in. This one moves it up. This one moves it left. This one flips it over the x-axis. This is the next one. G of x is equal to f of -x. Now let's guess at what this one does. If the negative on the outside flips it over the x-axis, the negative on the inside should flip it over the y-axis. Now this one's a little rare. It doesn't show up that often. So the negative on the inside will flip over y-axis. Or the vertical. And I'll explain what I mean by vertical later on. Alright, so that's 4 of the motions. There's more. There's only one more that I'm going to show you. Well, two more. There's 6 motions. Up, down, left, right, flip over the x, flip over the y, make it taller or shorter, thinner or fatter. That's the 6 motions you can do. 6 things you can do to a function. Alright. There it goes. Number 5. What happens if I take a new function and I say, let's make it half of f of x? Is it affecting the x value, domain, or is it affecting the range? The x values or the y values? The y values, because f of x is y, and we're taking half of all the y's. So if you do a little table, here's x, here's f of x, here's half of f of x. See if I remember what the coordinates are. -2, 0, 4. F of x was, where is it? -4? 2. What was the original ones? -4, +2, -2. +2, -2. There we go. If I do half of f of x, -4 becomes -2. 2 becomes 1. -2 becomes -1. Because we're cutting the heights in half. So the coordinates that we'd be plotting are -2, -2, 0, 1, 4, -1. This is when you wish you had graph paper. Wish I could have something I could stick on the board like graph paper. Let's draw the original one first. -2, -4, 0, 2, 4, -2. 4, -2, yeah. So here's the original graph, f of x. And then plot the new ones and see what happens. See what it looks like. -2, -2, 0, 1, and 4, -1. The domain's not changing. The domain is still going from -2 to 4, but the range has gotten shrunk. It's gotten half as high. Half as deep and half as tall as it comes closer to the x-axis. So I call this a shortening of the function. It's gotten a lot shorter than it used to be. That's because of a half. What if I put a 3 out front? What would that do? It would make it a lot taller. It would make it 3 times as tall in both directions. So depending on the type of number that you put out front, numbers between 0 and 1. In other words, numbers like 1/2, 2/3, 4/5, 0.1, 0.2, 0.3, something between 0 and 1, that'll make them shorter. Or closer to the horizontal. Closer to the horizontal. Let me write that in there. Closer to horizontal. It'll make it closer to the horizontal. If the number becomes bigger than 1, I should say absolute value, because it doesn't matter if it's positive or negative. Negative just flips it over the x-axis. If the absolute value of that number is bigger than 1, I really shouldn't say x. Let's change it to a. A is better. A. So this thing is a, that 1/2. If the number in front of the function is bigger than 1, then it gets closer to the vertical. It'll look like it's squishing up the y-axis when you make it taller. So it looks like it's getting closer to the vertical line. Alright, so it makes it taller, or taller. Alright, last motion, number 6. The hardest one. The one I don't usually put on a test. But it might crop up there because it's randomly chosen and all that fun stuff. The 6th motion is, what happens if I take that 2 and I put it on the inside, next to the domain? So now it's not affecting the range, it's affecting the domain. Anything that affects the range is usually very easy to work with. When it starts affecting the domain itself, it usually gets a little bit more tricky. So I highly suggest you take the inside and you set it equal to each one of the domain points. So 2 of x is equal to -2, 2x is equal to 0, 2x is equal to 4. Those are the original domains, -2, 0, and 4. If you solve all of those, you get your new domain. So, what's the solution to the first one? -1. Solution to the second one? 0. And what's the solution to the last one? 2. So those are the new domains. Then we're going to, of course, multiply by 2 and come back to -2, 0, and 4. Then we're going to plug it into our function and get our normal domain, our normal ranges out of it. And the normal ranges are -4, 2, and -2. -4, 2, and -2. But the points we're going to plot are -1, -4, 0, 2, and 2, -2. Draw it real quick. Original one, -2, -4, 0, 2, 4, -2. There's the original function. Draw the translated one, or transformed one. -1, -4, right? 0, 2, 2, get there, and 2, -2 here. This one took the graph and squished it. It still has the same height. It still goes up to +2 and down to -4, but the domain got squished. So this one, the number on the inside, this acts like an accordion. You know what I mean by an accordion, right? In, out, in, out. So when the number is bigger than 1, it goes in. When it's less than 1, it goes out. So it does exactly the opposite of what this one does over here, where if it's bigger than 1, it goes up, and it's smaller than 1, it comes down. So they're reversed, again, that domain and range thing. So when this A, we call 2A, when A, the absolute value of A is less than 1, this thing gets expanded. Along the x-axis. So it's the accordion going out. It's taking the graph and stretching it out. If the absolute value of A is greater than 1, then it gets contracted along the x-axis. So that's the accordion going in and squishing the graph into a smaller and smaller space. Does that make sense? I like the accordion. So the accordion on the x-axis is when it's on the inside. The accordion on the y-axis is when it's on the outside, if you want to think of it that way. Okay, so those are the basic motions that we can do. So let's put them all together. I don't have enough room. I need to erase. Everybody got this part over here, I hope. That's all gone. I'll leave 6 for a second. Now, once I get through this silly example over and over again, when I get to the functions I really want to talk about, we should be able to fly through them knowing what's exactly going to happen to each one of these graphs. At least that's my hope, my dream. So, for example, what happens if I take g of x is equal to -1/2 of f of x minus 3 plus 4. There's a lot going on here, but some of it we can kind of interpret what's going on. For instance, this plus 4, what is it doing to my original graph? Which way is it moving? Up. So this is going up 4. I usually just write U4. U4 or U4? What's the -3 doing? Moving it to the right. Inside you go opposite direction. So this is going right 3. Now individually you don't take -1/2. You take the negative first. This one tells you it's flipping. So it's taking any y's and making them opposite of what they were. So it's going to flip over the x-axis. Of course I'm going to call it a flip over horizontal. And the reason I do that is because if you move it up 4, it's not the x-axis anymore. It's a line that's 4 units up in the air, so it would be a horizontal line. Then the 1/2, what is that going to do? Well, it's the accordion, but is the accordion left to right, or is the accordion up and down? It's up and down, the height of it, right? Because it's affecting the y, not the x. It's on the outside. So it's the accordion on the outside, so is it squishing it down towards the x-axis, or is it pulling it further away from the x-axis? Squishing it, because it's a half. So this will be a squish instead of a pull. Books call the squish and the squash and the accordion a lot of different things, so it's better to understand which direction you're moving it in. All right, best way to do this, table. It really is. So the first thing you do is you say x minus 3, set it equal to your first domain value, which is negative 4. X minus 3, set it equal to your next one, which is 0. X minus 3, and set it equal to... Wait a minute, the first domain value wasn't negative 4. You're all letting me get away with that? It's negative 2, isn't it? Yeah, it's negative 2. So that's negative 2, then 0, and then 4. And then 4. And solve each one of these. That's the start of our table. X. The first solution is 1. The next solution is 3. Positive 3, because you'd have to add 3 to the other side. And then the last one is 7. Because you have to add 3 to the other side, and you get 4 plus 3. All right, and then the function is going to take this x minus 3, which is back to our normal negative 2, 0, and 4. And it's going to come up with a y value, f of x. And the normal f of x value is negative 2, negative 4. I erase it, so I don't... Oh, no, I see it. It's there. Negative 4. So it would be negative 2, negative 4, 0, 2, and 4, negative 2. Those are the original y values. Yeah. All right, then what do I want to do with f of x? Well, I want to take... Well, it's actually f of x minus 3. What do I want to do with f of x minus 3? Well, take... You might as well do both of them at the same time. Negative 1/2 of it. So what's negative 1/2 of negative 4? Negative 1/2 of negative 4. 2. Negative 1/2 of 2. Negative 1. Negative 1/2 of negative 2. I hear mumbling. 1. And the last column is, we just want to add 4 to everybody. So if you add 4 to everybody, 2 plus 4 is 6. Negative 1 plus 4 is 3. 1 plus 4 is 5. So the coordinates we're going to plot are 1 and 6, 3 and 3, 7 and 5. And then graph it real quick. Last one of this type. This is the hardest one. Originally, negative 2, 2, negative 2, negative 2, negative 4, negative 2, negative 4, 0, 2, 4, negative 2. So here's the original graph. And then the translated graph. 1, 6. 1, 6. It's up here. Next point. 3, 3, so 3 over, 3 up. Last point, 7, 5. So this is the translated graph, transformed graph. Is what it is. So if you follow it, it did move up 4 units, but you don't see it that way because it got flipped, and that's where a lot of people get confused. But it did move up 4 units. It definitely moved 3 units to the right. This point 1, 2, 3 to get to the other one. So it definitely got shifted to the right 3 units. The flip is obvious because it totally looks upside down. And the half is obvious because the green one is a lot taller than the blue one. So this blue one is the g of x function. Kind of neat, isn't it? Yeah. That's definitely one of my test questions right here.
Well, since you said that, where in the world did X values come from? I'm lost.
What, these x values?
Yes, the one where you said.
The problem is, the original function only works with -2, 0, and 4.
Where did you get those numbers from?
That's the original function.
But I thought you were starting a whole new example.
I kept doing the same graph over and over again. -2, 0, 4.
Okay.
Alright. So what you do is, if the inside gets played around with at all, it's best to take the inside and set it equal to each one of your domain values. And that gives you the real domain that you have to work with, or your transform domain. Does that make sense? So you have a transform domain, then you go back to your real domain. Because your function only works on the real domain, it doesn't work on the transform domain. So if you plugged in f of 1, it doesn't understand it. Because it only works on -2, 0, and 4. That's why I did that. Alright, it becomes easier. Because now we're going to talk about base graphs. And once we got all of these transformations out of the way, the base graphs are actually kind of simplistic. And I'm just going to give them to you. These are ones you have to memorize, sadly, but they're not that hard. The first base graph is the x squared graph. And if you forget the shapes of them, you can plot the general shapes, but here's the danger. The directions are going to be sketch the graph. You only get to plot one point when you sketch a graph. If you plot more than one point, I count it wrong. So try to get away from plugging in points and plotting coordinates because I will count it wrong right off the bat. A sketch is general shape. But before I get a sketch going, we're going to talk about generally what does the graph look like of x squared. And I am going to plot some points, but then I'm just going to draw it as a sketch. So let's plot some points. If x is equal to 0, y is also equal to 0. So you get the origin. If x is equal to 1, y is going to equal, well, 1 squared, which is 1. If x is equal to -1, -1 squared is also equal to 1. If x is equal to 2, 4 goes up a little higher. If x is equal to -2, 4 goes up a little higher. You get this general shape. It's called a parabola. So if I was going to ask you to sketch x squared, that would be wrong. Because that's not sketching x squared, that's plotting x squared. So a sketch of it would have to look like this. You plot one point, and the only point you plot is the origin, and the general shape of the graph looks like this. That's a sketch. So the first one is a plot of x squared, the second one is a sketch of x squared. That's what I'm going to be looking for. General shape and one point, location. Alright. Next graph. F of x equals x cubed. Running out of time for the quiz, too bad. Should we do the quiz or keep on going?
Keep going.
No, you don't want a quiz? Oh well. X cubed. It's a little taller. If x is equal to 0, y is equal to 0. If x is equal to 1, y is equal to 1. If x is equal to 2, y is equal to 8 goes way up here. If x is equal to -1, -1 comes down here. If x is equal to -2, -8 way down here. This graph has this kind of shape. It actually, if you zoomed up on a calculator, it actually flattens out as it gets close to 0. It actually gets very horizontal. It'll come down to 0, flatten out just a little bit, and then continue on its way down. So when I sketch the graph of it, all I'm going to be looking for is this. Goes through the origin, goes up on that side, goes down on that side. That would be a sketch of x cubed. It generally looks like this. F of x f of x equals the square root of x. If I was going to plot it, square root of negative 2. I squared of 2. Where am I going to plot it? This only takes what? Coordinate systems. Left and right, they're real numbers. Up and down, they're real numbers. I squared of 2 is not a real number, so I can't plot it. So it becomes not part of the domain. So what's the first number I can take a square root of? Ooh, what? 4 is the first number I can take a square root of?
0.
Way over here. 0. Square root of 0 is? 0. So we start at the origin. What's the next nice number I can take the square root of? 1. Square root of 1 is? 1. Next one I can take is 4. Square root of 4 is? 2. This graph kind of looks like this. Technically, it's the same shape as the parabola, lying on its side, cutting in half. It's the exact same shape. Our parabola rotated 90 degrees to the right, clockwise, and you get rid of the bottom half. That's what this shape turns into. So this is the square root of x. The sketch of it, of course, would lose the 2 points that I plotted up above and just have the origin. Just have the origin. 2 more graphs. F of x equals the cube root of x. It'll look long. Where x cubed was tall, cube root of x is going to be long. Why? So, what's the first cube root I can take easily? 0. And the cube root of 0, of course, is 0. Cube root of 1. 1. Cube root of 4? No. 5? 8. Cube root of 8 is 2. Cube root of negative 1? 1? Oh, negative 1, down here. Cube root of negative 8, down to negative 2. So this one has a shape that looks a lot like the x cubed graph, except it does the same kind of shape as x cubed, except vertically. It flips it 90 degrees and flips over the x. It does a double flip. But it's still kind of interesting. Again, the sketch of it would just have the point at the origin, and then going up on the right and going down on the left. Very level, flat, boring. All right, the last graph is the easiest. F of x is equal to the absolute value of x. It's a v. By definition, it's equal to x on the positive side, so that's a line with a slope of 1. It's equal to negative x on the negative side, so that's a line with a slope of negative 1. And you just get the origin, and a line going that way, and a line going that way. So it becomes a v. So it doesn't have any special curvature to it, it's just 2 straight lines. Okay, let me show you what you're going to do with these things. Let's see what you remember from the first long example. What if I have g of x is equal to x minus 3 squared plus 2? X minus 3 squared plus 2. What does the plus 2 do to the graph? It moves it up 2 units. So this is up 2. What's the negative 3 do? Right 3? Because it does opposite of what you think it's going to do, because it's inside the function. All right, so this graph, the only thing it's doing is going up 2 and right 3. So what do I graph? Well, we put a graph down. It's going right 3. It's going up 2. And I highly suggest you get used to this next step. Put in a horizontal line up 2. In other words, the line y equals 2. This becomes known as a alternate axis, or a transformed axis. We're going to go right 3, so we're going to put in a vertical line at x equals 3. Of course, x equals 3. The intersection of these 2 lines is guaranteed the only point you're going to plot. Everything else is just shape. So guaranteed, this point 3, 2 is on the graph. What's the general shape of this graph, though? Well, the overlying function is squared. So what's x squared look like? A u, basically. It's a parabola. So it goes up like this, and it goes up like that. And you're done. That's it. That's all I'm looking for. Can you say the easiest test question ever? As long as you know what the 2 and the negative 3 do, you're perfectly fine. So when does it get hard? Well, when I ask silly things like this. I put a few other extra little tidbits in there. You're not going to be doing it like the line segment graph where we were plotting specific points to come up with the shape. This one I'm only allowing you to plot one point. So you have to kind of show what's going on. Moving it 4 and the 2 is just like this, so that's not really hard. What becomes hard is that 2/3 that's sitting in front. How do I show that it was accordion one way or the other? So the way we're going to have to do this is, what is the negative 4 doing? This thing is making it go down 4. What is the 2 doing? Left 2. What does the 2/3 do to a graph when you multiply by it? Does it get it closer to the vertical or closer to the horizontal? Does it make it taller or shorter? If I take your salary and multiply it by 2/3, is it a bigger salary or a smaller salary? It's a lot smaller. 2/3 of your salary is 60% of it, 66% of it. So it makes it smaller. So this is going to get it closer to horizontal. Closer to a horizontal line. Now, what do I mean by the horizontal line is the transformed axis that I'm going to put in. So let me put my axes in, my new ones. This one is going to go down 4. So I'll put a transformed axis down here. This has an equation of y equals negative 4. It's hitting the x-axis at negative 4. It's moving left 2, so I'll go 1, 2, and I'll put a vertical line there. It's going to have an equation, of course, of x equals 2. So when I say closer to the horizontal, my graph is going to get closer to this line, y equals negative 4. But how do I show that the graph is actually getting closer to it? Well, I'm going to have to draw 2 graphs. One of them without the 2/3, and one of them with the 2/3. So the first one I'm going to graph it as a dotted line. So what does the cubic graph look like without the 2/3? What's a cube graph look like? Well, it comes up, goes through this point, and then kind of does a little swiggle through it, swoosh. So you're going to do a dotted graph through this point, and you say that this is x plus 2 cubed minus 4. It's missing that 2/3 part. So when I put the 2/3 part into it, how do I force that graph to get closer to that line y equals negative 4? Well, probably the easiest way to do it is pick a point. If I'm going to get closer to y equals negative 4, do I move in this direction or do I move in that direction? Number 1 or number 2? It's like the eye doctor. Number 1, number 2. Number 2 going down. So the graph is going to start here, stay on this side of the dotted line forever. It's always going to be lower than it, closer to the horizontal. When I get on this part of the graph, coming down to the negatives, pick an imaginary point on it. Which way would you move? Number 1 or number 2? Number 1, because it's getting closer to the horizontal. So the graph will go like that. So this would be g of x, the final answer. The final answer. Does that kind of make sense? Got closer to the horizontal, right? I mean, that's all you have to do is go, oh, I need to yank this closer to the horizontal, so you force the graph on that side. If it got closer to the vertical, you'd actually move it to this side, because that would be the vertical line you want to get close to. And this way, for that side, you'll pull it towards the vertical. Do I have time for one more? Not really. Oh. Homework. Quiz? You all want to stay here until 9, right?
Huh?
Huh? Yeah, I didn't think so.